In this video, we learn how to solve quadratic equations by graphing associated parabolas. This is not a hard topic, especially with the technology available today. My favorite would be either a graphing calculator or a website such as Desmos is good for graphing the parabolas associated with these quadratic equations. Okay, the hardest thing about this probably is the vocabulary. What is a quadratic expression? Well, it would be an expression of this form. Ax squared plus bx plus c. A, b, and c are any real numbers. A cannot be 0, otherwise there is no x squared term. And in fact, this is where the expression gets its name. There must be the presence of an x squared term and yet nothing of a higher power. So if I were also to have something like, I don't know, bx cubed here, I wouldn't call this quadratic anymore. Now here's an example of a quadratic expression equated to 0. So this is a quadratic equation. It's also said to be in standard form. Standard form quadratic equations are equal to 0, and on the other side they typically have terms in descending order from x squared to x to, when present, a constant term. Sometimes there's also a requirement that the coefficient in front of x squared, that the a, be positive. Sometimes that's not a requirement. It just depends upon who's writing the textbook. So any equation that has an x squared term in it anywhere, even if it's not in standard form, is a quadratic equation. And they will have at most two solutions. Sometimes only one solution, and sometimes no real solution whatsoever. One way to go about solving these quadratic equations, now again, a quadratic equation is where the highest powered term you see is x squared. And there has to be an equal sign, of course. One way to go about solving quadratic equations is make sure they're in standard form like this, and then go graph on Desmos or somewhere else the associated parabola. There's a curve called a parabola, and any equation that has this form will graph to be a parabola. We're going to see a lot of these curves today, and we're going to learn how graphing these parabolas can help you solve these quadratic equations. Okay, enough talk. Let's get on to a first example. Here we have a quadratic equation in standard form. See, it's equal to 0. And we're going to try to solve this by graphing this parabola. So all you literally have to do is go to Desmos and type this in, or to your graphing calculator. And you'll notice that this particular curve decreases to its vertex, and then it increases. And it's got two places where it contacts the x-axis. These are called x-intercepts. The ordered pair associated with this point right here is 2, 0. The ordered pair for this x-intercept is 4, 0. And if we've done everything right, the 2 and the 4 should be the roots to this equation. Now, why would that be? Well, because the idea here is that if we take 2 and plug it into here, it's going to make the y value, and we already know the y value is 0. We'll test that in just a minute. But if you're looking for numbers that plug in here to make 0, you can find them by finding these x-intercepts. So our roots, our solutions, sometimes they're called roots, sometimes they're called zeros, sometimes they're just called solutions, but in this case they are x equals 2 and x equals 4. There's 2 of them, and you will not get more than 2. And in some examples today you'll see that we get fewer than 2. We're not going to check both of these. Let's just pick one of these. I'll pick the 4, and I'll show you that in fact it is a solution to this equation. How do we do that? We'll just plug in the 4, replace the x with the 4, and tally all this up. So here's 16, here's 24, so I have 16 minus 24 plus 8, and this makes negative 8 plus 8 is in fact 0. So that's verification that we do have a solution. So it doesn't really get any harder than that. but there are some variations that we'll come across today. Here's another example. We are to solve this standard form quadratic equation by graphing the associated parabola like this. Okay, the work has already been done for us. We did it on Desmos this morning. Now, this parabola sits up a little bit higher than the previous example, and it only has one x-intercept. That x-intercept is 3, 0. And so, if we did everything right, that 3 should be the one and only one real solution to this quadratic equation. So I think we found it already. You can call it a root or a 0 or a solution, but there's only one this time, and it's x equals 3. And let's go ahead and test and make sure that that is an answer. So I plug 3 in to this equation and try to verify that that's going to come out to equal 0. Well, this is 9, and this is negative 18, and this is 9. So I literally have 9 minus 18 plus 9. Of course, that makes 0. And so that's why this is called sometimes a 0. Here's another example. Solve the quadratic equation in standard form, x squared minus 6x plus 10 equals 0, and do so by graphing the parabola. Well, so it turns out that this parabola sits up higher than the previous two examples. If you're looking for solutions by finding x-intercepts, you won't find them. In fact, this equation doesn't have any real solutions. Now, how do we know that? Well, the lowest y value you can get on this graph is right here at the vertex, and it's y equals 1. When we go to the right of this point, the y values start to increase. So they never get as low as 0. And so you can't find an x that you could plug into here to make 0. The lowest number you could make would be 1. So this problem has no solutions. So now we've seen examples of 2 solutions, 1 solution, and no solutions. And those are the only 3 possibilities when we're restricting ourselves to real number solutions. Now this parabola is a little bit different than the one that you've seen so far. It's inverted. It's inverted because of the negative coefficient that you see right there. Some would say this is not standard form because they don't like to have a negative coefficient there. Personally, I'm not bothered by it. But the solution to this equation, well, there's actually 2 of them, and they are, again, just found by graphing this parabola. And those solutions are found by locating the x-intercepts. They appear to be 3, 0 and 5, 0. And so if we did our work correctly, our solutions, let's call them zeros this time so we get more facility with the vocabulary. The roots, the solutions, the zeros are x equals 3 and x equals 5. This is pretty easy, isn't it? Now there are other methods for finding these solutions, but today we're focused on solving by graphing. Here's another example. It says write this equation in standard form. Okay, so the author of this problem must feel that it's not in standard form because we have to have a job to do, don't we? The problem is it doesn't say ax squared plus bx plus c equals 0 where a is positive. Right now a is essentially a negative 1. So what I have is this. And I guess what we need to do is somehow alter this equation so that there's not a negative 1 here. How are we going to do that? Well, we're just going to go to both sides of the equation, and we're going to multiply times negative 1. And when you're done, you'll have positive 1 x squared, right, because I have to distribute negative 1 times negative 1. Negative 1 times positive 8, well, it's going to make a negative or a minus 8. And finally, negative 1 times negative 15 is going to make positive 15. Now, what happens next? Are we in standard form? Yes, we are. Okay, so whoever made this graph probably went to Desmos and typed something like 1x squared minus 8x plus 15, and Desmos produced this graph, and then we can see that the roots to this graph are right here and here at x equals 3 and x equals 5, because the intercepts are 3, 0 and 5, 0. Now if this seems kind of familiar, it should be, because we just did a problem that had the very same x-intercepts and the very same roots. As a matter of fact, in the previous problem, we didn't bother making the equation a standard form equation. In the previous problem, let's go back and look at it, all we did was go ahead and graph this, and it produced this parabola that was an inverted form of the one we're looking at now. But it had the same x-intercepts. And the reason we're going to give you these examples back to back is to show you that transforming this equation here, like we did by multiplying by -1 on both sides, had no effect on what the solutions were. And it shouldn't. Okay, this one involves a little bit more work. This is not in standard form, but with just a little bit of effort we can make it look like standard form. So have we forgot what standard form is? Let's remind ourselves that an equation that looks like this, where sometimes the a is required to be positive, that is a quadratic equation in standard form. Well, to make this look like that, it strikes me that we shouldn't have a 12 over here. We should have 0. So the solution to this is subtract 12 from both sides. Now it looks like this. And even though there's no bx term here in the middle, I guess b is 0, and folks, this is standard form. And so this parabola over here was generated by going to Desmos and typing this into the equation editor. Desmos very kindly produced this parabola, and we can see the roots of this parabola are found at these x-intercepts. There are 2 of them. So again, the x-intercepts are -2, 0 and 2, 0, and that means that the roots or solutions or zeros to this problem are -2 and 2. Now, if we were to check our work, where would we do it? You could do it right here. You could plug either one of these in right here and find out that indeed, for example, the 3 times 2 squared minus 12 makes 12 minus 12, and that makes 0. But you could also plug these 2 roots or solutions back into here and check, and they would work there too. So the idea is, by subtracting 12 from both sides, we got a completely new equation, but it has exactly the same answers as this equation back here did. Okay, this next problem we're not asked to solve it, we're just asked to write it in standard form. There are 2 things that I think we're going to do. One, we're going to try to get 0 on the right side. So let's see, -x squared plus 2x equals 13. Let's subtract 13 from both sides. And on the right we get 0, and on the left we have these 3 terms, and no 2 of them are like terms, so you just write them down individually like this: -x squared plus 2x minus 13. Now for my purposes that's a standard form quadratic equation, but again we have a -x squared, and that may bother somebody. So what we'll do about that is try to convert this to a positive. And we'll do that by multiplying both sides of this equation by -1. And this is the second time I think that you've seen that. So let's go really fast here, okay? -1 times -x squared makes positive 1x squared. -1 times 2 is minus 2x, and -1 times 13 is plus 13. And on the right side we get 0. And by anybody's definition, that is a quadratic equation in standard form. Okay, just a couple more examples. Looks like we have 2 or 3 more. Write this equation in standard form and then solve the equation by finding the roots of the standard form equation. Okay, here's the equation given to us. It does not have 0 over here like we'd expect. the way to make this a standard form quadratic equation is to add 4x to both sides. Then these cancel to make 0, and on the left we have x squared plus 4x plus 3. And then to solve that by graphing, we would take the associated parabola that's produced when we type this into our graphing calculator or Desmos, and that would generate this parabola, and its x-intercepts are here and here. So we have -3, 0, and we have -1, 0. And so the roots to this equation, the solutions to that equation, are x equals -3 and x equals -1. Now, these are also the solutions to the equation given to us originally in the problem. And you can verify that, but we've done a lot of verifying today, so to keep this video short, we're going to keep moving. Here's a slightly different approach to graphing. And notice this is the same equation that we had in the previous problem. So I'll show you again. It's x squared plus 3x equals -4x. And in the last problem, I guess we were bothered by the -4x over there and the lack of standard form. So by adding 4x to both sides, we generated this. Then we graphed this equation and got this parabola and got these solutions. Now here's a completely different approach. You could probably get by in life without knowing this, but it's kind of fun. The idea is graph both sides of the equation. What does that mean? Well, it means going to Desmos and graphing y equals x squared plus 3 on the one hand. And that is the red parabola that you see over here. But also graph the other side of the equation, which is not a parabola at all. It's a straight line. And over here you can see that the graph of that is blue. Now, this time we're not looking for x-intercepts, we're looking for intersection points of the red and blue curves. And this appears to be -3, 12. And this one down here appears to be -1, 4. Now what you'll notice is that at these intersection points, the x's are -3 and -1 respectively. And those are exactly the same roots I obtained in the last problem by looking for x-intercepts. So again, this is just another way to do it. Graph this side, get a parabola, it might be red. Graph this side, get a line, it might be blue. And where those two lines intersect, go and look for the x values, -3 and -1. And if you trace down here, you'll see exactly that that last parabola in the previous problem had x-intercepts at those points. It's kind of interesting. It gives you a different way to do it. And now, I saw this problem. It's the same thing, it's just written a little bit different than the ones we've been looking at so far. It says, find the zeros of this function. Okay, what are they doing? They're asking you to solve this equation without really coming out and saying it. Okay. Because what they're interested in is x's that you can plug into here to get 0. And those 0 answers would calculate the f of x's, which by the way is just another way of writing y. So they could have given us the problem like this, but here's the idea. If you go down here and find those x-intercepts like we've been doing for the last 20 minutes, they are 1, 0 and 2, 0. Now, because those x's, 1 and 2 respectively, plugged into here generate 0 for y. Those two x's, 1 and 2, are called the zeros of this equation. Okay? It's the same thing, isn't it? It's just different packaging. Here's a problem that I saw on an assignment that my students are going to do today. And it's written exactly like this. It's a pretty poorly written problem, especially if they leave this off. Okay, if they only gave you these instructions, I would be scratching my head not knowing what to do, even though I've taught this subject for 30 years. Solve that? solve that? I mean, you really need to specify that what we're looking for here are roots or zeros. Because otherwise, I could set this equal to any other number. Like, for example, I could say solve x squared minus 3x plus 2 equals 5. And it's no more clear to me that that's what I should do than, okay, so here's where they pretty much deliver the specificity required for you to complete this. They say find the zeros. And that is what we did in the previous problem. So again, we're looking at the previous problem with just different packaging. And the solutions are, again, 1 and 2. Okay, finally, here's a problem that is not a quadratic equation at all. As a matter of fact, if you took this and multiplied it all out, you'd find out that it's a third degree. It's got a term that looks something like this in it. And it's what we would call a cubic equation. But we are to find the zeros of this thing. And what's been working for us all day so far is just go and look at X-intercepts. Okay, so we're stretching our imaginations a little bit, but it turns out that this method of finding the X-intercepts will solve this, as I'm about to demonstrate for you now. If there's an X-intercept of 5, 0, then x equals 5 is a root, probably the only root, for this function down here. Now, how would we test that? Well, we'd calculate f of 5 by plugging 5 into this, and we'd expect an answer of, yes, we'd expect y to come out to 0. So you put 5 minus 5 here, and over here you put the opposite of 5 squared plus 3 times 5 minus 3. Now, this is equal to 0 times, and it really doesn't even matter what this comes out to over here. I think it comes out to negative 13. But whatever it is, it doesn't matter because we're going to multiply it by 0, and that's going to make 0 for an answer. So when x is 5, f of x, or y, is equal to 0. And that's how this point was calculated. And 5 is the solution. And once again, we found it by looking for an x-intercept. Well, we're done here. Hope you enjoyed this. Maybe you learned something. My name's Eric. Have a good day.